Good evening, everyone. It's a great pleasure to host you tonight at the webinar organized by No Fluff Jobs Masterclass. I have a special guest tonight, Kirk Pepperdine, who's going to share knowledge how to program efficiently in Java, how to write efficient programs that are efficient memory-wise. Welcome, Kirk. Without any further ado, I'm passing the floor to you, and we're really looking forward to your interesting presentation.
For years, I've been speaking about garbage collectors, but quite honestly, I think in the next year or two, as as things have rolled out, we're going to see some really fun and interesting things happening in the garbage collection space that I'm hoping is going to make garbage collection less of an issue. It's still going to be a very interesting topic, but it's going to become less of an issue over time. That's what we've always hoped. With each new iteration of the garbage collector, and the question is, with the garbage collection issue sort of put to bed, what is the next problem that we're going to face? And unfortunately, this isn't the next problem. It is like the problem we've always faced, and so that's just what the little story here that I want to run through. So. We threw together that, but I imagine Tomek's already gone through that, so I'll just pass that, right? So, okay, so let's start with a demo, right? There's no better way to start a talk than to actually see some code running. So here I have some code, and now we're going to run it, and hopefully it will do exactly what I want it to do. I was fiddling with it just prior to. And what you want to do is right. So, okay, so there's a little program, and what it does is it actually says, okay, I want to, I want the program to guess this particular number, but this number actually represents an index into array of 3 choose 100,000 different number combinations. And so I'll just run it here, and you can see that it's doing. It's choosing, and it's making a guess, and it's filtering on the guess, and then it's using the previous guess with the answer, with the scoring I'm giving it, to say, okay, is this combination possible? If not, throw it away. If not, make another guess, and it goes all the way to the end until it finally says, oh, you picked, I think this is 0742,000 and something, and it's run in about 106 seconds. Well, you can't really tell the timing because there's all kinds of stuff happening here. But long story short, it took a long time. If I wanted to run slower, then what's the primary problem that I'm facing here? If I looked at my CPU utilization when this thing is running, you'll notice that it's running pretty hot. It was running 90% CPU. So you say, like, okay, something was algorithmically hot in this particular case. So what's responsible for this application running slower than I'd like it to run? Okay, now I'm going to go back to this. So we have a performance problem in this particular demo, and the answer is that the question is, what is your performance trouble spot? Now, in live presentations, I do a poll and answer questions and stuff like that, but for the webinar, unfortunately, it's a little trickier. So I'm just going to go on to the next slide and say, this is an industry survey that people have done, and it's a great survey and everything like that. So, and the people who've done it are good friends of mine, and they've done a wonderful job. But just look at the bubbles here, right? Just look at the size of the bubbles and what's there. It's like slow database. Some concurrency issues here, inefficient application code, whatever that means, right? But database shows up quite frequently, and this actually runs kind of strange from our perspective, because, well, actually we can explain what's going on here. But as you can see, in our experience from getting data from applications all over the place, we see excessive memory churn as being the primary problem, right? But you see, it's only a little small bubble here. It's like 10%, so what's going on, right? As a matter of fact, we're looking at approximately 70% of all applications are bottlenecked on memory. 60, 70%, something like that. It's a huge number. And it's a really big problem, right? And in this case, no, garbage collection is not at fault, right? So so how do you get this problem? Well, the question is, do you use Spring Boot, Cassandra, or any other big NoSQL solution for that matter? How about Apache Spark or any other big data framework? Log4j, or pretty much any Java logging framework in use today. JSON, I mean, who doesn't use any of these things, right? Or any other marshalling protocol where you're marshalling and unmarshalling. Who doesn't do that in microservice architectures? I mean, so as you can see, pretty much these are all things that we use on a day-to-day basis. And as we use these frameworks and as we write our code around these frameworks, what we're finding is that that's just going to push you right up into the 70%, right? So, and again, these are all very fine frameworks. They're very useful. But very few have been designed with memory efficiency in mind. As a matter of fact, I talked to the Hibernate guys at Christmas. We had dinner together 2 years ago, and they said, yeah, that's the thing that we want to push on right now is memory efficiency. Now, the other issue here is that we've been told GC is free, so go ahead and allocate. Allocate away, because you're not going to bother the garbage collector. And the truth is a little bit more difficult that, right? Because while allocations are not expensive, they're not free, right? So we can still have issues with memory, and oh wow, there's another issue here. Is like, oh, we actually do have issues with the garbage collector when we start allocating heavily, as we'll see later on, right? So here's some war stories. I don't really want to dwell on them too much, but the one I like is nice because this took us 1 day of work. We went from 400,000 TPS to 25 million just by working on the allocation rate in the application, right? And this is very typical of what we see. We're just not seeing percentage increases in performance when we tackle this problem. We're seeing integer multiples in the increase of throughput in applications when we start seeing, finding this problem and working on it to solve it, right? So, 400,000 to 25 million, it's a bit extreme, but certainly a 1 or 2 or 4x is generally easily achievable in most of these applications. And you'd be surprised at how easy it is to do it. Okay. So what are we looking at? Well, okay, so everybody talks about garbage collection, and we'll talk a little bit about that, just to remind ourselves what's going on here. But, we're trying to find these. Now, when we get these allocation sites, we're going to see that they are mostly going to occur on a fast path, hopefully. So you get a fast path allocation, really cheap, as you'll see. Sometimes we'll get pushed out to a slow path. And it might be possible that certain classes of objects can be optimized in what's known as a scalar allocation, which means we're not going on heap at all. And that's perfect, right? If we're not on heap, then the allocation pressure reduces and we get a lot of benefits from that. Okay, so just to remind ourselves of what we're actually dealing with here, you can see this is a highly generalized Java heap, where we have a Eden space, or what we call a nursery. We have a survivor space. We have a tenured space, right? So Eden is where we create things. Survivor is where we hold on to things for a little while. And tenured space is where long-lived data should be, right? Now, each of these spaces, since they have a different role in memory management, they all contribute to a different set of problems. And all of these things will affect GC overhead. Okay, now why are we talking about GC overhead? If GC is not the problem, well, that will come out a little later on. So we have an application threads are going to allocate in Eden, and let's just discuss what's happening here. So this is our Eden space. We're going to have what's atop of heap pointers. So the allocations are going to do what's known as a bump and run on the pointer, right? But if we simply do a bump and run on the pointer, then we're going to have a hot pointer when we have multiple threads trying to allocate into heap. So what we want to do is we want to just reduce the, turn the temperature down on the pointer. And in order to do that, what we're actually going to do is we're going to introduce this thing called a thread local allocation block. So as we see, we have foo equals new foo. So we're going to say, okay, do we have a Tlab? No. Okay, so let's do a bump and run on the top of heap pointer, grab a Tlab. So that's a buffer that's ours, and we can do the allocation into that. It's going to have our own Tlab pointer in there. And so I can say, well, I need, I think, 100 bytes for foo. So I'm going to bump the pointer up 100 bytes. So now that buffer is mine. Part of the buffer is mine. So what I can do is I can just fill in the data. Bang, we have our allocation is complete, right? So you can see it's fairly quickly, right? I'm just going to possibly have to grab a Tlab. If I already have the Tlab, I'm just going to do a bump and run on a pointer. That pointer is mine, so I don't have to do anything in terms of fencing it, right? So I have to have fences on the top heap pointer, but not really a big issue. Fill in data. Pretty much we're done. So I have a second thread. It's going to do the same thing. So this is like wash, rinse, repeat, right? Bar equals new bar. Grab the Tlab, bump my pointer, fill in my data. And that's pretty much like a fast path allocation. Just, that's what it looks like. If I have a byte array, then I'm gonna have to go to a slightly slower path because maybe this byte array is bigger than the Tlab, which means I'm gonna allocate that out into general heap. So I need to bump top a heap pointer, allocate my byte array in there, and then life is good. Okay, so the reason why the byte array is, of course, a bit more expensive, it doesn't fit in the Tlab. That means we need to work with this top of heap pointer, which might be slightly hot anyways, depending upon how many threads that you have. And certainly if you have hot allocating threads, then that's going to be a fairly hot pointer or a hot spot in your application. And in this case, we're concerned about that just because that's a synchronization issue. Okay. So what happens when you get to the end of the Tlab? Well, this is when things get slower. So there's this thing called a Tlab waste percent. And if you happen to be over the threshold, then that's cool because, the allocator is going to look at it and say, oh, I need to go get a new Tlab, right? Now, if you're below, but you're too big to fit, then you're going to try the allocation, you're going to fail. And when you fail, then you're going to say, okay, wow, I need to get a new Tlab and then do the allocation in the new Tlab. But you can see the failure path is much longer. And so that puts you down a slower allocation path. Okay. Now for generational spaces, you're going to have to do more work when you allocate in these particular spaces. Now, typically it's the garbage collection threads that are going to do the allocation in the space. Now this is for a generational heap, but for the regional heaps, the work is different, but there's still extra work. So I'm just going to describe it this way, right? So allocations and tenured are going to make use of a free list. And there's also some other data structures that they need to maintain in terms of tracking pointers and things like that. But the point is that when we start allocating from a free list, we're no longer doing a bump and run on a pointer, which means we need to search the free list, find the slot that's big enough, then do the free list manipulation that gives us access to the memory in the heap, and then grab the memory in the heap. And then, so the explanation is longer. So obviously the time to take it is longer. So as you can see, the estimate here, it's approximately 10x the cost of doing a bump and run in young generational space, right? So we don't really want to allocate here very frequently. So we just want long-lived data in here. The next point is escape analysis. So how do we get scalar replacement of our objects? Well, I'll show you an example of this in the code because this is actually important as we talk about how to find these problems when we go to fix them. But escape analysis generally asks the question, if I'm going to allocate this piece of data, how many threads have access to it? If I can definitively prove that only one thread, the thread that created this data, is the only thread that can access this data, then I can treat that allocation differently. If that allocation happens to be small and really only contains primitive values, then what I can do is I can just not bother allocating on heap. I can just take those values, the fields that you define for that object, and basically inline them right in the code. Or if I'm not going to inline them in the code, I might be able to register hoist them. But basically there's a bunch of things that I can do that really says that this allocation now is really, really, really cheap because it's not going to trigger the entire mechanism that we need to go through in order to allocate this data on heap. Okay, but the key here is that data can only be visible by one thread, which means that scoping in your application is important. If you have a very narrow scope for all your data, then there's a good chance that escape analysis is going to recognize and say, okay, I can do something with that allocation to make this less less expensive. But if you have globally scoped, then it's going to fail escape analysis, and you're on heap for that allocation. Okay, so I talked about
short question. So you're saying to limit the scope is one of the great. So limiting the scope makes it efficient. The other thing is, if we mark it final, does it help?
Okay. So no, because final variables can have visibility to many threads, for one thing, and the other thing is that marking variables final that final information doesn't really make it down into the compilers in the runtime.
Mm-hmm.
So the runtime doesn't know final is final because in the runtime final isn't final.
Sure.
Okay.
And exactly. So exactly, I wanted to ask this question because this is a common stereotype kind of with these final variables. There are like people who are actually, fighting to make everything final because of optimizations and stuff like this. And so is there any practical advice apart from limiting the scope that we can, like, what could we do to make, the escape analysis, like, make, like a piece of data visible only to one thread, or to help the compiler actually see it this way?
It's really about localizing the call to a single method.
Okay.
If you can do that, if you can localize the data to a single method, then escape analysis will work well for you in general. Okay. In terms of the final question, final means copy on write. And copy on write tends to exasperate the problem. It makes it worse. Okay? Yeah. So it's not to say don't use final. There are plenty of reasonable uses of final. So, I mean, with everything you do, there's always a reason or a reasonable use. It's just understanding what the costs are of making that decision so that you can make an informed decision rather than make a origin-based in theology, right? Yeah. I'm going to use finalology as my term here. Yeah. Right? Make everything final. Yeah, that comes with other consequences.
Yeah.
So good questions. Okay, thank you. So let's talk about the problems here. So with high memory churn rates, that means we're creating many temporary objects. So that means we're going to quickly fill Eden. That means we're going to have more frequent GC cycles from collections of Eden. We're going to speed up the aging process. So how does data get into tenured? It survives so many collections. If the collections are happening frequently, then the data gets into tenured sooner. And think of it this way. If I have data that I know is going to be in memory for 30 seconds, the question is that in young gen where it's cheap to collect or free to collect, or is that in tenured where it gets expensive to collect and causes young generational collections to be more expensive? And the answer is, I don't know. How many garbage collections ever run? So if you speed up the aging, it's very likely it ends up in tenured space where we don't want it to be, and it doesn't stay in Eden, right? And that's called premature promotion. And there's a couple of different types of premature promotion. There's ones that you can see and ones that you can't. So the accelerated aging creates the hidden premature promotion problem. But that premature promotion problem gets down into more frequent collections of tenured, which we've already said is going to be a lot more expensive. So allocations in tenured more expensive, collections of tenured more expensive. So you can see increased allocation rates leads to more expensive this, more expensive that. There's a whole basket of things that just become more expensive, right? Increased copy costs, increased heap fragmentation, which is increased frequency of compaction, which is more expensive. So allocation is quick, is the other issue, but quick times a large number equals slow, right? So if we're spending a lot of time allocating, also, I mean, that's another issue. Aside from the effect on garbage collection, it's just like every time you allocate, you know, it takes some time. And if you're doing that at a high frequency, then of course, you know, that you're going to be spending a lot of your time allocating and not much time executing application logic. Right. So as I've been hinting in the last slide, what happens is that we're going to really put the pressure on these two things. So it means we're going to hyperact the garbage collector. So if we hyperactivate the garbage collector, you know, the question is, you know, how does that show up? And well, it shows up in GC cost. So GC cost is a fixed cost per collection plus a variable cost depending upon the amount of work that we have to do for each collection. If we collect frequently, then generally the variable cost will come down, but the fixed cost is always there. So overall GC cost is going to be cost times frequency. And as you can see, if we up the frequency, then the overall GC cost is going to go up. And then because of that, everybody starts blaming the garbage collector, right? It's the garbage collector's fault. And the reason why I spend so much time on this is because even after you have these conversations with people, they'll start talking about tuning the garbage collector, and you're going like, no, no, you know, leave the poor little garbage collector out of here. It's, you know, stop blaming the garbage collector. It's not the garbage collector's fault. It's the developer's fault, right? They have built memory complexity into their application. And what we need to do is, of course, is to deal with that. Now, right. So one of the things that we do to try to help with this situation is we're saying like, okay, well, if GC frequency is an issue, let's just turn down the frequency of collections. So how do we do that? Well, if we have a bucket and we're filling that bucket at 1 milliliter per minute, then of course the number of minutes to fill it is, you know, just dependent upon the size of the bucket. So if we don't want to empty it, we'll just make a bigger bucket. And that's just all we're going to do here. We're just going to say, let's create a bigger Eden. Now we're getting into memory over provisioning issues. And, you know, that's a huge issue when we get into cloud environments. Our VMs or JVMs are using much more memory than we would like them to. So do you see how this is all spilling out now, right? So we're over provisioning our JVMs to manage this, which means our VMs are bigger, which means that our cost is now much greater than it should be in order to host our applications in cloud environments. And, you know, or we need bigger machines if we're on physical hardware. So everything all is now coming back to, you know, basically, you know, we have this issue. We're gonna oversize Eden, right? Okay, so we probably said some of that, right? So we need a measurement to try to figure out, okay, so when do we have this problem? And so we can look at allocation rates, we can look at the number of bytes that are allocated, but we're really not concerned about the number of bytes because, you know, for some reasons, what we're concerned about is the frequency at which we hit the allocation site in our application. And generally what we see is that, you know, the allocation rate is a power curve looking thing, and there's many reasons why it's this type of shape, but, you know, really, in this case, what we're saying is that when we get above 1 gig per second, we're sort of in this red zone where this is a real problem. And if we can drive that down as close as we can into about the 300 megabytes per second range, we know we're going to get these huge gains in performance. Now, it's actually worse than this, but maybe I'll explain that in a minute, right? Because really what we're saying is that this idea of oversizing Eden to slow the frequency is really a Band-Aid over the problem, right? This is really something that, you know, that doesn't really solve the problem. And actually it's worse. Can I explain how it's worse? Believe it or not, it's actually worse than that. So think of it this way, right? Like I got a single socket on the motherboard on my chip, right? You know, so my CPU is plugged into this, and, you know, I got all my VMs running, and I got one hot allocating thread in my Java application. So what it's going to do is it's going to allocate, but of course all of this data has to be pushed out to memory. And so how does it get out? Well, there's a on the back edge of the chip, there's a memory, memory write channel that goes over the bus and puts things into memory, and that's all wonderful, right? But I can have one hot allocating thread basically stuff that entire channel up, which means now the chip has to throttle itself so that it doesn't overflow the buffers. That means it slows your application down. Okay. Now, it doesn't just slow your application down. It slows down every single thing running on that machine, because I'm going to clock back that CPU, right? So you're not just blowing your JVM out of the water, you're blowing everybody else's JVM out of the water that's running on that piece of hardware. It's part of the noisy neighbor problem, but it's a hidden problem, right? So really starts getting really bad really quickly.
So what you're saying, just to recap, is that if we write bad code, we're gonna slow the whole machine down. Not only your program, not only the JVM, but we're gonna slow the hardware down because it's gonna throttle itself.
Yeah, that's pretty much the story.
Yeah.
It really gets fun, doesn't it?
Yeah.
Okay, so the other problem is like, okay, we have large live data set sizes. So this is another side of the equation, right? So, so if we have high memory churn, we're going to tend to have an inflated live data set size because we'll have more loitering, as I call it. So this is objects hanging around for longer than they should be, and that will cause its own set of issues. We get inflated scan for route times. We get reduced page locality, more paging, in other words, or having to go through what's known as translation look-aside buffer lookup things in order to figure out where these pointers are actually pointing to. Inflated compaction times, increased copy costs, less space to copy to, right? So, yeah. So, and here's the whole thing, right? In terms of pause time, the chart on the left is heap occupancy over time. The chart on the right is pause time. You can see the correlation here between pause times and heap occupancy. The solution here is try to reduce your footprint of your application as much as there is. I mean, other than that, I mean, in terms of a technical tuning, there is no solution. With the high allocation rates, we can make Eden bigger, but you really can't change anything until you change your application code. But but at least we can tune the JVM to sort of cope with it. But with high footprints, then then there's you just have a big footprint, and that's all you can do. There's unstable live data set size. Essentially, you might have a memory leak, or session leak, or loitering objects, or something like that disturbing it. Of course, unstable live data set size, if you go to the next slide, means that I'm going to run out of memory. Or, if I tune it so I don't run out of memory, you can see that as the heap occupancy grows, my pause times are just going to grow, and GC overhead is going to get higher and higher and higher. And of course, all of these things are really things that need to be solved by altering your application code. So what I'm going to do is I'm going to do a little bit of analysis here and just try to say, okay, here it is. So here it's running at about 5.2 gigs per second.
Okay.
That's the current allocation rate, right? So it's certainly clearly above the 1 gigabyte per second rate that we're seeing. And as you can see, it's still running. And I think we had it running at about 110 seconds or so prior. In the previous run. I didn't record it, and my bad. But anyways, it's certainly well more than 100 seconds. So the question is, what is the issue here? What is preventing this thing from running like it should? Oh, here we go. It's actually going to finish shortly. Let's get a timing out of it under these runtime conditions and see what it says. It'll probably be a bit noisy, but if I was to run it again, there'd probably be a big variance, but who knows? Yeah, that's 111, it's 112 seconds. Okay, see if you can remember that. Let's get out of here. I'm going to drop here. I'm going to quit this. I'm going to say, okay, let's run it again. Okay, and unfortunately it's coming up here. And let's say, okay, well, let's find the problem. Okay, so how are we going to find the problem? Well, I wanted to use a profiler. So I'm going to bring up Visual VM.
Okay.
Okay. And with Visual VM, what I'm going to do is I'm going to, okay, it's, of course, oh, it's up on this window. Awesome. Okay. I'm going to attach to the process. So here's our game that we're playing. So, and I'm going to go over to the profiler, and I'm going to say on memory settings, look at the filtering to make sure the filtering is set up all right. There you can see the help is saying how the filtering is set up. Since I don't know what I'm looking for, I'm going to look for everything.
Yeah.
Now I'm going to go to instrument with memory, and here's the trick. Since I'm looking for allocation frequency, and I don't really have a good frequency measure here, I'm just going to use allocated objects as a proxy. So I'm going to focus on the number of objects that are being allocated. Okay?
Yeah.
Awesome. Now, go back to my application. Of course, we're just going to run it. And I'll just slap that over on the side there, and we're just going to watch what happens. Okay. And we can see that we have two candidates that are standing out from the list. And that's a mutable big integer and an int array. How's that? So those look like two likely candidates, right? Okay, so I'll give you, we can talk about things, about a bunch of different things that are going on here. The one thing is this application runs what I call bimodally. Now, what I mean by that is that I have one hot code path when it's guessing, but it's not printing anything to the screen, which means that the guesses are failing the filtering. Okay.
Yeah.
Then we have another mode where we're actually printing things to the screen, because in that mode, what's happening is that the guesses are passing the filtering, which means that they're possible solutions to the problem. Okay, so this thing runs bimodally. Each mode in your application is going to have a single bottleneck. So everybody talks about bottlenecks in their application. The honest truth is that you're going to have one bottleneck per mode in your application. Now, if your application is fluctuating between different modes all the time, then of course you might see different bottlenecks expressed at different times. Now, and the bottleneck is actually going to be the sum of the pressure that's applied to the hardware. And so I know from this particular case that, since we run bimodally, that there's going to be two bottlenecks here that I'm going to have to find, or potentially have to find. Okay, so I think we found the first one. So let's take a snapshot. The bottleneck in this particular application is obvious now, running in the mode that we're running in. Since we're not running in the other mode yet, the other bottleneck is not obvious, but I've taken a snapshot here, and I want to focus on the second bottleneck first, because that's interesting. And then we'll work back and solve the obvious bottleneck and see what that does. Okay, so this is actually the bottleneck, or the thing that the profiler says is a bottleneck. And so we can look down and see this and say, well, okay, there's the constructor, there's the constructor for a score, and it's being created in this board is possible solution method. So the class's board is possible solution, and that's where that allocation site is. So we can actually go into the code, and we can go to board, and when I look at board here, I can say, okay, here's is possible solution, and you can see that there's where my score is being created, and I'm going like, oh my gosh, what person could possibly have written this code? Like what rookie programmer could have written this? Because as you can see, the score is being created over and over and over again in this loop, right? And that's simply bad code. So we'd think like, okay, so, what would we do with this? Well, okay, let's just hoist that code out of here, right? And we can say, well, okay, I want to reuse this thing, so let's try score.reset. Bang. Okay, so that looks like a reasonable solution, right? The
And
fun
can
thing
you
is,
maybe show us the score object kind of definition? It has this int array probably, right?
well, if we look at the score is just two counters and a Boolean.
Okay.
One that indicates that I have the correct number in the correct column, and the other one to say I have the correct number, but it's in the wrong column. Okay. And a jackpot says I have all of the numbers and they're all in the correct columns. So
Okay.
that would be a jackpot condition. We got the answer, right? But there's like 3 primitive values here. And so when you come back to board and look at it and go like, okay, what's going to happen is the compiler is actually going to just get, first off, it's going to hoist this allocation out of the loop. And the second thing it's going to do is it's just going to scalar replace this whole thing, right? So we're not even going to get an on-heap allocation. So the question is, why is the profiler highlighting this as an allocation hotspot when the compiler in the runtime looks after it? And the answer is escape analysis will recognize this in the runtime as being locally scoped. So I can do all that. As soon as I add a compiler, the compiler instruments the code. And part of the instrumentation is to pass the object into the compiler, into the profiling code itself, so it can do stuff with it. Means 2 threads are looking at it, which means we fail escape analysis. So by adding the profiler, we've created an allocation site out of something that the JIT would have taken away.
Yeah, so that's a super interesting point. Let us maybe recap the reasoning here. So basically, this would have been fixed by the compiler if we hadn't used the profiler. But since we're using the profiler, there are like 2 threads that are watching this object, and it means that it can't be fixed and kind of taken care of by the compiler, which makes this code actually run much lower, which eventually can actually lead us to the conclusion that basically, if we are using profilers, in some cases, we can actually be generating and solving problems that aren't there.
Exactly. Right? This is where the profiler is actually misleading you.
Yeah.
And so one of the things you have to do is understand how your profiler is working and understand what to do. So in a longer version of this talk, we could actually do a study of what the JIT compiler is doing to the code and compare that to what the profiler is telling us. And that will tell us definitively that this is not a piece of code that we need to worry about. So I don't have to do all this work here, right? And there's other spots in the code where I don't have to do any work. And actually that JIT compiler study is interesting because it can actually point out to places where I might be able to make some adjustments to the code and get better JIT code out of everything, right? So it's a worthwhile study to do in large code bases. Okay, so let's go back to our hotspot here, which is our int array, and this is a real hotspot. So if we look at what the JIT compilers are doing with this, we can see that, yeah, there's nothing it can do. So it's doing the allocation of this particular array, and you can see it's doing it in this mutable big integer. There's a constructor. It's doing some math here and math remainder. Oh, right. So we're into this like domain code here. It's like math remainder stuff. Yeah, not sure what that is, but it looks like I'm trying to do some math with indexes because I'm calculating an element index. So remember I said this was a lookup in an array, but the array doesn't actually exist. So I'm taking the index and transforming it into the into the number. These 3-digit numbers that are showing up here. Oh, hold on. Let's look at the profiler over here. Yeah, see scores come up. That's because we're running in the second mode right now.
Okay.
Yeah, so there we can see scores come up. Okay. Okay, cool. So what does this mean here? So if we look at this arrangement group, calculate index, you can see, where is it? Calculate element index, remove symbol. Okay, so yeah, there's okay. Okay, this code's now complicated and a bit, we might say, ugly. Oh, it's recursive too.
Okay.
So yeah, so I mean, so if we look at all of this and stuff, you know, then we'd have to work through the logic and see what's going on here. Oh, here's a remove symbol. It looks like, oh, we got loops here where we're creating like it's essentially lots of new array creation, interarray creation in here. And I think if we go back in here, we can see there's some copy of range. Oh, that's still big mutable integer. Somewhere we're using big mutable integers. That's got to be maybe in the math class. Let's go into this math class here and say, oh yeah, okay. Oh, we're using index. Yeah, okay. So anyways, so we can basically like, you know, walk through there it is, our big integer value supporting our index class. Anyways, so we can walk through the logic and sort of sort things out and stuff like that. But, you know, long come to short, this is where the problem is. This is where algorithmic complexity is. And this is the thing that's driving our high allocation rates. So what I want to do is I want to fix this code. So I'm going to cheat here a bit since I already have the fix coded. I'm just going to comment out the good code, the bad code, and comment out, I'm not going to claim, okay, I'm going to comment out the bad code. I'm not going to claim the code I'm replacing with is good. I'm just going to say it's better. Okay, so let's go down here and let's comment out this stuff here. And so in this case here, what I did was I did some things to just reduce the number of calculations that are being done so I can achieve the same effect. And we got rid of, also got rid of this piece of code, which was generating a whole pile of interarrays and things like that. So we just reduced the memory complexity of the application. So let's shut things down properly here. So we can finish this up. So I'm going to stop profiler. Actually, I'm just going to kill this profiler now. I'm going to stop the application. Yeah, yeah, don't worry about that. And we're just going to rerun it again. So I restarted the application here. So I'm just going to set the conditions the same. Okay. And I'm going to run the test and boom, baby. Look at that. Are we smoking or what?
Yeah.
Are we smoking?
Yeah, it's definitely going much faster.
Yeah, it's like, you know, I think we're down to like about maybe, well, certainly less than 20 seconds. So we went from like 112 seconds to, well, yeah, say 20 seconds in this whole thing, right? And I just got rid of and all I did was get rid of that allocation hotspot. So if we look at the GC log again, you can see that our allocation rate should be significantly lower. So we've taken off a ton of allocation pressure. And, you know, so the thing is, if I look at, yeah, look, see, we're way down. We're like 500 megabytes per second. So 550, certainly less than a gig. Meaning that if I want to make this application run even faster, solving this problem is probably not going to be the answer. So I need to look at what the next bottleneck is in the application and then start working on that.
Sure, sure. And I think it's a super interesting observation. Like, I think to people that were not exposed to these kind of problems is the, you know, like the practicality of what you're showing, like about, like, you know, the allocation rates in terms of megabytes and gigabytes per second. I think maybe you can share a bit more, you know, how you generate, like, you know, how you got the GC log file and why is it so important? Yeah, because people may not know this, and, like, you know, why is it important? Like, you know, why, how did you get the number of 300 megabytes per second? Why is it kind of like an industry standard for a quick or memory efficient application versus like 8 gigabytes a second? Why is it slow?
Okay, so yeah, and that's a good discussion to have. We have 1 minute left on the webinar, but we can, if you want to answer the questions, we can go over a little bit.
Sure.
So there you can see the parameters I used. Generally, I use more than this, but for this particular problem, it's okay. So I get the GC log. I use this tool, which I've written, it's Sensum. Unfortunately, it's not generally available today, but we're hoping before the end of the year that it will be open sourced. So that we'll have access to this type of tooling. And so what I do is I take the numbers that are found in the GC logs in terms of what the heap occupancy is before and after the collection, and we do the math on them. And then that gives us an approximation of the allocation rates. Okay, so that's pretty much.
Yeah, so you're just checking how much space is taken on the heap before and after
the garbage collection.
Yeah, after the garbage collection, and you just kind of like take these two numbers, compare them, and see what the difference is.
That's correct, and then I divide it by the duration.
Yeah.
Right. The runtime of the application between the two collections.
Yeah.
Right. From the end of the last one to the beginning of the one I'm looking at. Okay. And so, and that gives me an allocation rate. Now, this is the fun part, right? So the ability of the chip to clear memory, to clear the buffers and write to memory, is dictated by the bus speed of the motherboard.
Yeah.
And that value hasn't changed much in the last, I don't know how many years. And it seems to be fairly consistent across all motherboards that are in use today. So that 8 gigabits per second doesn't really matter what service class of hardware you're on. That seems to be a fairly consistent number across all bits of hardware. Which is odd. You wouldn't think of it that way, because you're thinking like, wow, I got Xeon CPUs over here. It should be like ripping. And yeah, okay. Yeah, they go much faster, but they still get backed up on the right, because it's not the chip at that point, it's the bus.
Sure.
And the bus speed is tied to the memory chip speed, so it just means that memory chips are not getting faster. So I don't know what the speeds are on DDR5, but DDR4 we get a bump, and DDR3 we get a bump. But you can see, as the newer chipsets come out, they tend to focus on power, because that's important for laptops, and more people are buying laptops, and they want longer battery life, and they want more memory, and so power, not speed. But of course, speed is also important. So you can get good DD4 low power chips for your laptop, but try getting a DDR5 chip for your laptop. Not likely. Yeah. But it does matter in server environments. We can still use them, so you get a bump. But so that number will go up, but I don't, by how much I'm not sure yet. And that gets to the other point. These numbers are drawn from experience. We generally tune on the order of thousands of JVMs per year. So if you do that for a number of years, then you can imagine that we see a lot of patterns across the industry. And the numbers I'm giving you are just the result of our experiences tuning all of these applications.
Great, Kirk. Thank you. Thank you so much. I think that it's a great takeaway for all the participants here and also watching on Facebook live stream. It's definitely a great takeaway to understand, what allocation rates, what they are, what they should be in order to make your application memory efficient, and how it was calculated, and from what it's actually taken. It's limited by the hardware speed, and that was a very, very interesting and great explanation. So thank you so much for it. Unfortunately, we have to finish right now. So thank you so much for this excellent knowledge sharing session. We're really honored to host you during this webinar, and we're really looking forward to watch and learn from all your videos in your No Fluff Jobs Masterclass track. We're going to be sharing more of this in-depth and practical knowledge about garbage collection. So thank you so much, and we're really looking forward to that.
Thank you for having me here, Tomek, and it's been a pleasure trying to demonstrate some of the work that we've been doing for the last, I don't know how many years. Thank you. Thank you all for attending.
Thank you. Dziękuję bardzo wszystkim uczestnikom. Pozdrawiamy serdecznie i zapraszamy do No Fluff Jobs Masterclass. Dobranoc.